All right, ready to start the presentation.
Wait, Dean, can you run the slides?
Oh, sorry, I thought you were done.
Yeah, I showed all mine, but not in the room. This is Jonathan's over here on the end. He's going to be doing the meeting on the queues and SQL.
Well, I ran through them online. Okay, so the next slide is the Data Saturdays and SQL Saturdays one-day conferences. And you could just go to datasaturday.com or SQLSaturday.com. And then the next slide is about the past conference. So they're the dates in November, and it's you just do Google Past Data Community Summit 2023. Like I said, it's only going to be in person this year. The past couple of years, they offered a virtual attendance, which was nice. And then the last slide is all about Dan and his experience. And take it away, Dan.
All right, can folks hear me okay? I'm not sure how the audio is going to work here today. Everybody's good? Excellent. Let me get my PowerPoint fired up here. And my apologies for the delay. I had an issue connecting to my email, which in turn meant that I didn't have the link to the Teams meeting. So hopefully we'll be able to make up some time, but probably I'm going a bit long, so my apologies. So today I'm going to talk about SQL Server table partitioning. Table partitioning is a feature that's been around since SQL Server 2005. I've used it extensively since it was initially introduced in that version, and come to learn some gotchas, surprises, and I'm willing to share that stuff with you today. But one of the most common misconceptions about table partitioning is it's going to automatically improve performance of large tables. That's not necessarily the case, and that'll be a theme of the presentation today, is that, just indiscriminate use of partitioning can actually set you back. Have performance regression if you don't think about what you're trying to do with partitioning. But that being said, partitioning does have a lot of benefits as well. So you just have to pick and choose whether or not it's suitable for your particular situation, your workload. So today I'm going to cover some of those objectives, discuss some partitioning concepts, a little bit about view partitioning, which is what we had to do before SQL Server 2005 introduced table partitioning. I'll talk about table partitioning in detail, as well as how to automate some of the table partitioning management. One of the reasons that large tables are problematic is simply because you can't get your offline or your maintenance done within your maintenance windows. Partitioning allows you to target specific partition level operations so you can work on subsets of data, whether or not that be index reorgs or rebuilds or changing data compression options. You have a lot of tools in your tool belt when it comes to partitioning by leveraging individual partitions of a larger entity. It can reduce the intermediate space requirements that are needed to rebuild indexes and those sorts of things. And you can also separate active data from read-only data. That allows you to, for example, use a fill factor of 100 on your historical data that, to compact the data quite a bit, and even do, additional compression options, while, having the active data that's constantly being inserted, updated, deleted, whatever, have a, more appropriate fill factor, so that it just let the page splits occur, and lets free space be allocated where it's actually needed within the table, and then only after it's that interval is closed, then we can go and reorg the table, or reorg that partition, I should say, as it becomes a historical partition. And one of the reasons that you may want to implement partitioning is to reduce your RTO for very large databases. Like if you have a database that's many terabytes or in size, as you probably know, it can take quite a while to restore that thing. And if you have a large table with where you need to have the more critical data online and available sooner than the old stuff, you can use piecemeal restores with a file group strategy, such that you restore the primary file group and the active file groups, for your large partition table first, and then follow up with the historical data. Of course, the historical data isn't going to be available and queries will not be able to get to it, but at least they will be able to find or get to some of the data, the more current data, with that kind of a strategy. And I mentioned that you can have more granular control of those individual partitions. And another benefit of partitioning is, being able to load or purge or archive data based on subsets of the table rather than the entire, table itself. So for example, one of the first demo I'm going to do is going to speak to how to, just do a quick partition switch as part of an ETL process, so that you don't have to, you can use an ETL process to load a table that doesn't even have to be partitioned, and then use a switch to move that partition from the staging table directly into the primary table without, incurring a large amount of downtime while the table gets loaded. And partitioning allows you to keep all the historical data in the same table rather than moving it around into a separate table for archive purposes. Although you can still, do archiving in conjunction with partitioning, the question I would have is, why do you want to? If you can keep the, the older data in the same table, there's really not much downside to doing so. But again, I want to underscore that final asterisk that when it comes to performance, it's really query and index tuning that are your main tools for improving performance. And also, using features like column store, compression, those sorts of things as appropriate. Table partitioning, at least when it comes to an OLTP workload, rarely will just improve performance just by doing partitioning alone. And it can actually, as I mentioned, introduce regression for performance. So just, again, I just want everybody to have success with table partitioning. Just don't just jump into it and expect things to suddenly get faster. The idea with partitioning is that it should be totally transparent to DML queries, inserts, updates, deletes, selects, merges, that sort of thing. And what it does is it separates rows of a single entity, aka table, when you're talking about table partitioning here, horizontally into subsets based on some column value. Commonly, that column value is a temporal data type, like a date or time, or a date time data type. And I'm going to concentrate on that most today, because that's the most common scenario that I've seen for table partitioning, and probably provides the most utility in the wild. I've used that a lot of different scenarios for table partitioning, and just about every one has used a date time column. The partitioning column determines what partition a given row goes into, and SQL Server uses that partitioning value to find which partition to access for a given query. And it affects the way the SQL Server, database engine accesses data within a partition table as well, within the query plans. Let's see, make sure I got the right slide there. Okay, yeah. So with the regular non-partition table, assuming they have a clustered index on the table, the table itself is organized as a B-tree index, and that's what we see on the left-hand side. And if you have a non-clustered index on the table as well, you'll have a B-tree for the non-clustered index. Both those structures are part of the same table, and they're all in the same partition. Now, SQL Server, since 2005, the storage engine considers all tables partitioned from a storage perspective. And that's what allows you to actually switch data in and out of a given table, even if it's non-partitioned. It'll actually just move all the extents from one table to another, all of the aligned, B-tree indexes that are part of the table, as long as they reside on the same file groups, the same physical storage. It's a metadata only operation, so it happens very fast. With non-partition tables, as you likely know, you can specify what file group the entire table or index gets created on. You can use a switch to move all the data and indexes from excuse me, a non-partition table into an empty table, as long as it has the exact same identical schema and the index and compression options are identical between the source and target, and they're on, again, the same file groups, meaning that they're storage aligned. So, that's how you can switch things, very quickly. But one gotcha, and I like to mention all these gotchas through personal experience, is that don't forget to update statistics whenever you do a switch or truncate. Because even just a regular truncate with a non-partition table, that does not remove the stats from the table. So the stats immediately become stale. You have an empty table, but you'll have a stats histogram that, has the distribution of values before, when the table used to have data in it. And same thing with switch. A switch is basically similar to a truncate in that it removes all the data from the table, but it doesn't alter the stats blob for the any stats that you have on the table and its indexes. So whenever you do a switch or truncate, key takeaway is do a update statistics afterwards. All right, so jump into a demo here. All right, so I prepared the before the presentation, I created a table with 100 million rows in it. And this is just a regular old-fashioned non-partition table, nothing fancy about it, just has a few columns just for demo purposes. And then I have a staging table that's exactly like it, in terms of the schema, and it's on the same file group. So here I'll just, recreate the staging table, make sure everything's empty. And right now, before I do anything, have 100 million rows in one table, and of course the staging table is empty. So normally here I'll just show you the statistics just to underscore the point about the stats. So the source table has a histogram with statistics associated with it, but the staging table doesn't have any statistics at the current time. So I can move all the data out of the primary table into a staging table, just as a single atomic, auto commit operation here. And as you can see, that was instantaneous, and that moved all 100 million rows from the primary table into the staging table. And if I do just a regular select count, you can see that. But again, if I look at the statistics, the original table still has all the same statistics on it, but the staging table, it doesn't, even though it has all the data now. So typically what we would do is, if, let's say we had an ETL process and you wanted to minimize the downtime of the primary table, what you can do is, truncate your, your staging. Here I'm kind of doing a little backwards here, but anyway, what you can do is just truncate your target table and then switch the, the table, in. And here I'll just do it as part of the transaction, and I'll update statistics as well. So that was a sub-second operation to essentially load 100 million rows from a staging table into the primary table and update statistics on both tables. I mean, typically you wouldn't need to update statistics on your staging table, except it depends on your ETL process. If you actually use that staging table as part of like a merge operation or something to prepare it before it gets put in there, it might have statistics that could affect the subsequent ETL processes. So since I did the switch and that table became empty, I went ahead and updated statistics as well. Now this time around, since I've done that, the statistics are going to be, correct in, both those tables. And as you can see, I update statistics so it has a full, histogram range associated with it. And of course, just to prove it, I do have 100 million rows in the table. Any questions so far? All righty. So just speaking about the execution plans, a couple of, gotchas that I want to mention. Again, I try to sprinkle my demos with some things I've learned from the hard way in real life here. So here, it just looks like a simple query, in both these cases, just to return. I prepared these tables such that each of these will return. I think it's 8 rows, if I remember right. Let's see. Yeah, so we have, even though there's 100 million rows in the table, each customer only has about 100 orders spread throughout the entire table, historical orders. But I have, 1 million customers, so that adds up, and that's why I have 1 million rows. So if you look at the, let's see if I had the execution time on there. Okay. So these are 3 tables. Let me back up for a second. So I have I have the same data for this customer in 3 tables. In the tables, one table only has 1,000 rows, one table has 1 million rows, and the other table has 100 million rows. So the table size varies quite a bit, although the data that gets returned is the same, because it's just a matter of the number of customers, not the number of orders per customer. So if I'll include the actual execution plan for these 3 queries. And again, the schemas are identical, it's just that the data is different. So if we look at the execution plans, I'm trying to get a handle here, there we go. Yeah, so we look at the execution plan, it's just a simple index seek, because I have a good index for these things. And if I look at the, whoops, I forgot to turn on statistics.io. Let me repeat that. So for each of those, the same queries, each of which returns 3 rows, it only had 2 logical reads against the 1,000 row table, only 3 logical reads against the 1 million row table, and 4 logical reads against the 100 million row table. The point being that, it's really the indexing that determines the performance regardless of table size. Your logical reads go up slightly as the number of index levels grows because of the table size, but performance-wise, that extra logical read is going to be, pretty much imperceptible. So even though it's a relatively large table with 100 million rows, it's not partitioned, and it, performs reasonably well. Now, if I, run the same queries basically, except without the where clause on the, the timestamp, in this case, since there's not a limiting, I basically, I'm going to have to touch the entire table. And even then, it's only a few logical reads, per table, because essentially all the rows are fitting into in a single page, because I don't have 100 rows per customer, or 2 rows per page maybe, and that's why that first one's a liar. But again, it's all back. It's the indexing that's really helping the performance. But things start to change when if I have to do a scan. Like in this case here, I don't have any good index to be able to support this query. So, I'm just doing a simple select count query. So if I look at the execution plan, it's doing a full clustered index scan to do the aggregate, and it's parallel on top of that. So if I look at let's see, this is just this 100 million row non-partition table, had 13, had more than one thread. So, scanned, had to do that many scans in order to, or there are that many threads scanning the table. Now the same query, I'll just jump ahead a little bit. Now this is against an identical table, except this one's partitioned. When I run this one, and I don't have any, date, or if I do have a date criteria, you know, in this case here, it was able to eliminate some of the partitions, you know, but still, because it's a parallel query, it still, you know, did, you know, multiple scans. But the number of logical reads, if we look at those between on those two, it's roughly, yeah, it's roughly what, about 10% of that, because with the partition table, with the scan, it only had to scan the needed partitions. It didn't actually have to scan all the partitions of the table, you know, contrasting where the non-partition table without a useful index had to, you know, scan the entire table from beginning to end. So this is a case where, you know, for more of a reporting or an analytical workload, even without a supporting index, your queries could benefit with, you know, from partitioning. If it's, you know, assuming that there's a, you know, criteria on the partitioning column, which is, you know, like I said, commonly is going to be a temporal, you know, data type. Skips that, interested in time here. So with SQL Server, before table partitioning, we had to do partition views, and I'll briefly cover that because it could be that you're in a situation like I was in my first table partitioning endeavor, where I had a partition view and I needed to convert that to a partition table. And fortunately, it went very, very well, although I did run into the gotcha of not updating statistics afterwards. So initially, after we did the release and, you know, converted it to a partition table, performance was horrible, to the point where the application was absolutely unusable. And then I updated statistics and everything went swimmingly well thereafter. And that table was, I think, 30 to 40 billion rows and multiple terabytes. And it really, the partitioning really helped the manageability quite a bit. It was already indexed properly, so the, you know, in that case, the, you know, partitioning really didn't help or influence performance much. But, you know, when you have a multiple terabyte table, it's really nice to have, you know, the flexibility to, you know, have the, you know, partitions, you know, individual partition level operations. So we could actually then rebuild the index at the partition level and didn't have to, you know, go through and do it for all, you know, 40 billion rows. Let's see, is anybody running anything before 2016 here? So everybody's 2016 or later? Of course, Julie always.
I'm not partitioning or anything on that. And it's packaged software.
I know, Julie's always behind on technology. Yeah, obviously, you know, if you're constrained by, you know, vendor, you know, software, you don't have much of a choice. But you know, so I'm going to assume that everybody's on SQL Server 2000, you know, 16 or later, you know, aka a supported version of SQL Server. I think 2014 might still be in extended support. I don't remember now, but I don't use anything that old. And also regarding partitioning is available in Azure SQL database and as well as managed instance. And you know, it's a real handy feature. So with view partitioning, the old-fashioned way, you pretty much just create a union all view of a bunch of tables that have identical schema. You create a check constraint on the partitioning column of each member table to make sure that a row will only exist in one of those tables. And those check constraints are set up to be mutually exclusive so that, you know, the row can exist in exactly one table. And you could theoretically even have different schema, different indexing on each of those tables, but in practice, you pretty much would make everyone identical. You know, that's kind of the use case that I had when I first did my initial partitioning endeavor. The partitioning column has to be a part of the primary key in order for the view to be updatable. You know, it's a union all view. And in the case of distributed partition views, aka, you know, in a federation, you can actually, you know, wire those, you know, You can have, you know, linked servers and tables on each of those linked servers to essentially do a little bit of a scale out kind of a scenario. I personally have never used distributed partition views, you know, but I just want to mention that they're available. But that's a way you can, you know, scale out, you know, your read-only workload, you know, with the same entity. You could also, of course, with or without partitioning, you know, use always-on availability groups and to, you know, scale out read-only workload on the compute side, but on the storage side, you would still have full tables on each of those nodes. And then in order to yeah, add or remove partitions, you pretty much just have to change the view and, you know, create and drop the underlying tables accordingly. I'm going to skip through the whole partition view, DDL, and execution plans because we got started a bit late and I have a lot of stuff to cover anyway. But just to compare and contrast view partitioning and table partitioning. With the partition view, you can have gaps in the partition ranges. And then if you ever try to insert a row into the view and there's not a place for that data, that row, then it's going to error out. With a partition table, you cannot have gaps. There's always a partition for every possible column value. You can have a different, you know, schema with the partition view on some of the member tables, but with a partition table, you only have one schema. So, you know, there's no provision for you having different, you know, a different schema or different indexes on certain partitions or anything like that. See, partition view, you can end up with untrusted check constraints if you're not careful when you do your bulk operations. But not so with SQL Server table partitioning because partitions are always trusted. You know, the storage engine guarantees that you'll never get any data in a given partition that doesn't belong there. The optimizer has to go through a lot of work. I skipped through that one demo where I showed the partition view, but essentially it has to, you know, do all the work for all of its table to optimize the query. So if you have a partition view with 100 tables in it, it's going to have to, you know, it's a much more complex query plan just due to the nature of the number of tables and the different indexing it has to evaluate. With table partitioning, the partitioning column is used like a seek predicate. So, you know, even though it's not technically index column or doesn't have to be, it'll be the first predicate that you see in the seek operator. It'll look for the actual partition column. You know, so it's not like with the view partition where every query every table will have it'll just use the regular B tree. You know, it's not really using the partitioning at that point. So typically, you'll create, you know, partition tables that are what I call, or what's called align. Align meaning that the table and the non-clustered indexes are all partitioned, you know, similarly using the same essentially partition, underlying partition function. And when you do that, you'll end up with, you know, a structure that looks something like that, where each, you know, B tree component, because you know, the table itself being a clustered index will be a B tree, and its non-clustered index will be in one partition. Then there's a independent partition 2 with a boundary between those two. And those partition boundaries are really what determines what rows go into which partitions, which I'll detail in a second here. But the important part is that, you know, with a partition table partition table being aligned, that allows you to use the switch and partition level truncate for a lot of the maintenance operations. If you have a requirement where you don't have an aligned partition table, then you won't be able to use, you know, partition level operations for the, you know, truncate and switch. So SQL Server in the query plans, we use the partition function to essentially it'll evaluate that and use that as part of the seek predicate to determine which of the partitions it actually touches. Certain DDL operations, like a alter index, truncate switch, can work on individual partitions, and that's all about manageability. Table partitioning is range partitioning by nature. Unlike some other DBMS products that have like list partitioning and hash partitioning, range partitioning is really just defining defining the boundaries such that the data that goes into a given partition is determined by the boundaries on either side of that partition. And I have a couple of graphic slides to kind of show that in a minute here. Now you could do list partitioning just by creating a check constraint such that only exact values could be placed in the table that align with the partition boundaries. But I personally haven't had a use case to do something like that. I guess if you had like a multi-tenant system where you wanted to be able to have every customer, let's say, in its own partition, you could engineer a solution like that where your customer ID would be the partitioning column, and of course all your queries would typically specify the partition ID or the customer ID in the queries, so you'd be able to only touch the partition that they needed to. Hash partitioning you could do with just doing a persistent computer column to materialize the hash value, but personally, I don't think that's really appropriate in the SQL Server relational world, because then you're really just sharding, and there's no logical relationship between a given row and the data that it represents. Usually, you want the partitioning column and the other columns in the table to be logically associated with something, whereas a hash value is just an arbitrary number, if you will, and it would allow you to distribute the workload across different partitions, but ask yourself, what value would that really provide? I mean, if your storage is all commingled, in the same SAN, and anyway, it's really not going to provide a whole lot of value performance-wise. So to implement, table partitioning, Microsoft introduced a couple of objects. You have a partition function and a partition scheme. The partition function defines the partition boundaries, and the partition scheme defines the file groups that are associated with each partition. Essentially, it's a mapping of partitions to file groups. One thing I will mention up front here is that, a lot of people, or a lot of the examples you'll see use user-defined file groups and place each partition on a different file group and so forth. In Azure SQL database, all you have is a primary file group. So you have to put everything on the primary file group. And I'll go so far as to say on most on-prem installs as well, when all your storage is on a SAN, unless you have a really specific reason to not bother with user-defined file groups with your table partitioning. It's only going to add complexity that, in my opinion, is unneeded unless you have a specific benefit by doing that. Like in the olden days, people used to always put indexes on this different file group than the data. But remember, that was back in the days of spinning media, when hard drives only had about 1 or 2 gigabytes of storage. I mean, that goes way back. Nowadays, with modern storage subsystems, the utility of file groups is, mitigated greatly. However, you still though would want to use user-defined file groups if you needed to do a piecemeal restore. So if your objective of partitioning is for reduce your RTO through piecemeal restores, then you would need to use user-defined file groups. But generally speaking, I would suggest always put everything on the same file group, just for simplicity, and makes things a lot easier to manage.
Yeah.
Oh, yes, sir.
Another point for keeping your partitions all in the same file group is that if you want your switch statements to be true metadata only and complete quickly, they need to be on the same file group. If you switch partitions from a partition that's on one file group to another file group, then you have to actually eat the IO cost to move the extents.
I gotcha. So yeah, to paraphrase the comment, you know, in order to, when you have multiple file groups and when you switch between one and the other, you're going to have to move the data.
Right.
Pure and simple. It's not automatic, because all a file group is a abstraction layer. It's a name for a set of files, and ultimately the storage under which it resides on. So the key points of a partition function is it defines the data type of the partitioning column, range specification, meaning right or left, and I'll detail that in a minute, and the boundaries between the partitions. The partition scheme is associated with exactly one partition function, and it specifies the list of file groups with one entry per partition. So even if you partition everything to your primary file group, you'll have a list of file groups as part of the partition scheme, all of which are going to be primary, because you have one per, you know, boundary, or I'm sorry, one per partition. And when all you got to do to partition the table or index is to, on your on clause, just specify a partition scheme instead of the actual file group. There are some limitations on your data types. You can't have, you know, the deprecated text or end text image data types. You can't have max data types, you know, CLR, etc. You can have up to 15,000 partitions in a table. However, there are some implications for having more than 1,000 partitions. So I would recommend that you try to keep under 1,000 partitions unless you have a specific need. And you know, there's some guidance in online documentation related to partitioning, you know, about that. Essentially, it requires more memory, you know, et cetera, to manage those indexes, especially when you have not aligned indexes. So try to keep it under, you know, 1,000.
Yeah.
Yes.
For the number of partitions and everything. So, I mean, if we have to like keep that in mind all the time, we have to create like dynamic partitions so that every time, you know, it goes closer to 1,000, and the partition group itself like changes based on, I don't know, like if we're using ID number, if there are 100,000 rows, when it goes to 100,001, then we're gonna increase the partition size by adding more IDs and reshuffling the partition itself. Is that something that you're saying we should do, or how do you? I mean, like beyond going without partition, how do you like mitigate that effect?
All right. So the question is, how do you work around the 1,000 partition limit? In this, you know, presentation, I specifically focus on the temporal partitioning, you know, sliding window kind of scenario, where it's based on a date time column. So usually you'll know what those are in advance. And to avoid any sort of, using dynamic scripts, if you will, not necessarily dynamic scripts, but scripts that, you know, altered the partition, you know, function and scheme, you know, on the fly as part of a regularly scheduled partition maintenance process, which I'll cover in more detail later. But if you're partitioning on something that's not temporal, which I think your comment kind of applies to your question, you know, let's say it's an identity column and you want to try to get 1,000, or I'm sorry, let's say 1,000,000 rows per partition is your goal. Then once you get to a certain size, you know, you say, well, I'm over my 1,000 partition limit, or maybe it's the hard limit of 15,000 partitions. You want to redistribute that. So that means basically recreating everything from the ground up. That essentially is a method of sharding. And like I said, I'm not a big fan of sharding. It doesn't really fit well, very natural in the relational database world. because by splitting up really the IO into each partition and doing so evenly, what have you actually gained? You know, as opposed if everything is, you know, already kind of commingled on your storage subsystem. Like for example, if you're in Azure, you don't have much control over that placement of that, you know, storage. If you're on-prem, you're probably on a SAN, and, you know, unless your storage administrators are, you know, specifically laying out the LUNs in such a way that each partition, you know, is, with solid state storage, matter of fact, I think it actually calls this out in the Azure documentation, where there's no penalty for random access versus sequential access on IO. And that's really would be your reason for trying to segregate storage, is to have random IO workload on one volume and sequential on another on spinning media, because in the olden days of spinning media, when you interrupt a sequential operation, that disk head has to move, and that is very costly. I mean, multiple milliseconds for, you know, your disk IO time. And if you're doing a lot of IO, you know, you're kind of dead in the water, because, you know, you just saturated your IOPS. So all that being said, I haven't personally had a use case where I've run into the need to, you know, repartition, you know, data based on, you know, like, you know, an ID type value.
Even if this date time, say, I mean, 1,000 partitions is like basically 3 years worth of data.
Right, I was going to mention that too. So what I would do in the case of a temporal one, let's say just for sake of argument, you're doing daily partitions, and the reason you're doing it is because you have an incremental daily load, you know, which is not uncommon. So what I would do is have, you know, like daily partitions for the most recent data and near future data that I'm about to load. And then, you know, periodically, you know, combine or aggregate the daily partitions into a monthly partition, and do so as part of a regular maintenance job. So you might have, for example, your daily load process where you just incrementally load your, you know, daily partitions, and then a monthly job where you start a new month, you create, let's say 30, 31, you know, partitions for your daily, for the upcoming month, and you rebuild the, you know, the partitions for the, well, used to be the completed month. You just, you know, make it a daily partition. Unfortunately, I don't have an example, you know, demo in this deck to do that, but the strategy that I would use is create a staging table to switch out all of your 30 days, your full month of daily partitions, so that it only has those 30 partitions. But I would start with it having the same partition function as your original table, then, but with a different function name. Then I would do a create index with drop existing on your clustered index to essentially make it a monthly partition, you know, using a different function, and then switch it back into the main table. Yeah. So unfortunately, like that's a relatively complex example, but it's something that you could do to work around the 1,000, you know, limit or ideal without.
That's great. That's great. Thank you. Really switch to do this partition.
Yeah, and there's a lot of different ways to get that done. A couple other questions here.
Yeah, is there a range of data in a table in which a partition has substantial benefit? Otherwise, if you haven't approached this range of records, a partition really just adds nominal benefit.
So I'm not sure I fully understood the question when you say range of records.
Yeah, so in your demos, you had a table of 1,000, 1,000,000, 100 million.
Right.
So I can understand the value of the partition with a table of 1,000,000 or 100 million records. But if you have a table with just 1,000, 100, and you know that that particular table is very unlikely going to reach 100,000, a million, 100 million records. Would a partition really add just nominal benefit to managing those records, or is it, no matter what size of the table it is, partitioning definitely has substantial benefit?
In my,
More sense?
yeah, I think I understand better now. So my answer to that would be, if you don't have a problem, don't fix it.
Okay.
I mean, that's really the short answer, because if you can get all your work done within your maintenance windows and your table is, multiple terabytes, more power to you. I mean, we have online, index rebuilds and stuff now that, can still get the job done. But, you don't necessarily have to, don't feel obligated to implement table partition just because it's big. And in terms of real small or smaller tables, I should say, the additional administration complexity, in my opinion, doesn't warrant probably microscopic improvements for manageability. It's my take on that.
All right. Thank you.
Was there another question? Nope.
I was just trying to point out.
Oh, okay. Yeah, it's hard for me to see with the backlight here, so sorry.
Yeah, what do you go about?
Let's see. Lost track of my slide here.
So I actually do have another question.
Sure.
So if as just part of your organizational policy, if you're constrained on making actual changes to database objects, could you create a partition on a table function, inline table value function, or something like that, or a table variable, so that you're not making real changes to the actual database object?
I'm not.
Irrespective of the value, but like, is the only option you have is a table partition or view partition? There are no other database objects that you can put a partition on.
So the question is, are there any other objects that you can partition? I can't think of one. Is the short answer. I think, at least I've never thought about it, honestly, because in terms of like a table variable or a table type, you don't have an on clause. So there is no sort of, notion of, table partitioning there. And yeah, I'd have to have a concrete scenario to really speak to, more intelligently. So, yeah. So as part of the partition function specification, it has a, and this is one of those gotchas that I want to call out. It has a range specification, which is either left or right. And that determines which adjacent boundary includes the, or which partition includes the partition boundary value. Over time, what I've learned is, especially with temporal types or any incremental type value, you're usually better off using a range right partition function. And unfortunately, the default is range left. It's just range right is just a lot more intuitive, because I think of an incremental value like you're always adding partitions on the end. Whereas with the range left, you're always adding partitions before the partition that you're splitting. So it's kind of, shall I say, awkward. So the examples that I have here, I do have a slide that shows the range left stuff, but in terms of the DDL examples, everything is, going to be range right. But some of the gotcha is that, or the reason, or the considerations for the range is that it determines what partition gets created when you split an existing partition. If it's a range left, the partition gets created to the left of the partition that you're splitting. And if it's a range right, it gets created to the right of it. It also determines what happens when you remove a boundary from the partition function. When you remove a boundary, you're essentially removing a partition. not deleting it, but you're moving the data from the partition that you're getting rid of into the remaining partition, and it determines what direction that data flows. With a range right, when you get rid of a partition boundary, then it'll be moving the data to the partition on the right, or the next higher partition number. Whereas on a range left, it moves it the other direction when you remove the boundary. It also determines the when you create the the partition scheme, you specify at least one file group, and if you start with a partition function with no boundaries, and you still need at least one file group on your mapping, which let's say it's the primary file group. Then when you later add partitions, you add additional partition partitions to the function, as well as another additional file groups to the partition scheme, which could be the same file group primary. But what gets people messed up with that is that you can never remove the first partition from the from the partition scheme, with a range right, and you can never remove the last partition from a partition scheme, or last file group, I should say, from a range left partition. So it's just kind of something to keep in mind of. The reason I mention that is because I've seen people, especially when they use user-defined file groups, I'll have year 2017, 2018, I'll name my file groups like that. Then I'll create my partition scheme, and it may be true initially the first partition had 2009 or 2017, one per year thereafter. But later on, when time comes to, well, this is a sliding window, so I don't need 2017 anymore. Well, there's no way to remove that 2017 year file group from the partition scheme, because it's the first one in the case of a range right. Or if you were going the other way, and let's say if it was a range left, your last year, let's say, is 2023, and then there's no way to get rid of that one out of your file group, even in 2024, 25, etc. So just be advised, and that's another reason I don't like to use user-defined file groups for table partitioning, unless you're using that like a piecemeal restore type scenario, because it's not intuitive, and I've seen people do that a lot. And another gotcha with the range right or range left, I don't think I called that out here, I probably should have, is that well, I'll mention that on an upcoming slide here. Oops, sorry about that. Yeah, I just want to make sure I spoke to that. Okay. So when it comes to implementing partition, you can have a single partition function that's shared by multiple partition schemes, and you can have multiple tables and or indexes use those partition schemes. The partition scheme is really what determines whether or not a given table or index is partitioned and how, ultimately, and then the partition function is just one level higher than that. If you have at some point, you're going to decide, if you do table partitioning, you're going to need to decide, well, should I have one partition and function per table, or should I have multiple tables share the same, let's say, monthly partition scheme? My recommendation for that is to, if you're always going to be sliding your windows or doing your partition maintenance at the same time, in other words, those tables are logically related, then you should probably use the same function in the scheme. However, if you have unrelated tables that you want to partition monthly, you're probably better off having those be have separate objects for those separate partition functions and schemes. Let's see, trying to Yeah, whenever you add or remove a boundary from a partition function, it essentially cascades to all the associated partition schemes and the underlying tables and indexes that use those schemes. So that's why, you know, plan carefully so that you don't end up with you know, inadvertently affecting many tables and indexes when you know, do your partition maintenance, unless that's what your intent is. Yeah, so here's just a slide that just shows some DDL for the partition functions. So in this case here, I have two boundaries, both for, you know, one for 2017, one for 2018. And as a result of those boundaries, I'm going to need 3 partitions. So you always have one more partition than you do boundaries, because the boundaries are really just the, they're between existing partitions. So if you think about it, like if you start with a single partition with no boundaries, you're going to still have one partition. You add one partition boundary and then end up with 2 partitions, etc. You know, so just be mindful of that. You always have to have one more partition than you do, you know, partition boundaries in your function. So with the range right, it really is functionally, it's saying that the partition on the right contains the boundary. So if you want to express that as, you know, as a comparison operator, you're really saying that, you know, the partition on the left has values that are less than the partition boundary, and the partition on the right has the values that are greater than or equal to the partition boundary up to the next partition boundary. And then the same applies where, like in this case here, the first boundary is 2017. So this partition will contain everything that's greater than or equal to 2017 and less than the subsequent boundary, which is 2018. So that way, all the values for a given date end up in the same partition. Even though this, in this case here, this is a date time data type. So we have both date and time values in it. And the gotcha when it comes to range left with this setup, if this were a range left partition scheme with those exact date boundaries, or more specifically exact year boundaries, it would end up with data for, you know, you would end up with data on exactly the first day of the year end up on the partition on the left, aka in the wrong partition, if you will. You know, so you would have to use different boundaries. Like, for example, for the range left, you would have to use, with the date component, you would have to have the highest possible value for that time component. So you would have to say, you know, using, you know, 23, you know, for the time component, it would have to be, you know, the, you know, like in a date time 20, which doesn't have any milliseconds, I'd have to say 23:23, I'm sorry, 23:59:59, you know, for a range left. And in my opinion, that's not very natural. So yet another reason to do a range left, I'm sorry, range right for these. So this is what you end up with that slide. By the way, I had a mistake on my slide where I didn't update the dates on some of these. I updated the DDL, but not the graphic. Yeah, so it didn't match exactly. And yeah, and here's that same example I just spoke to, where, you know, if you use a range left function, just be sure that your boundaries specify the highest possible value for that, you know, day, you know, rather than exactly midnight. Yeah, I'm running pretty long here, so I'm gonna have to try to play by ear to skip a few slides. So I already spoke to that. Let's see. Yeah, this is, so let me just do partitioned table DDL. Oops. Okay. All right, so this is the DDL I used before I, you know, for this demo. is that I created a range write scheme on a datetime to data type. So it has, no milliseconds associated with it because I want to save a couple bytes of space because I don't need milliseconds in this case. But here's the, a script that'll actually create, my objective here is to have 36 full months of history plus the current month, that's 37 partitions, plus the future month, so that's 38 partitions. And then you need to have that permanent partition I mentioned, the one, the catch-all partition for old data, anything older than the last, retained date. So that's a total of 39 partitions. So I ran, this script to create the, the partition function. And in this case here, I'm just also just partitioning everything to the primary file group. I have a table, nothing fancy about it, but it's partitioned on the order create time. And then I loaded that 100 million, row table I discussed earlier a little bit. But there are some gotchas here. Like I said, I like to mention gotchas. So when you're using, Management Studio, especially to look at execution plans, be extremely cognizant of data types and literals, especially when you have literals here. Some of the like your application code is most likely going to execute parameterized queries if you're following best practices for performance and security. In Management Studio, unless you go out of your way to execute a parameterized query by using SP execute SQL, you may have different behavior between query plans that your applications use versus what you have in Management Studio. So here, if I run this query here with the actual execution plan, we see, it doesn't look too bad, with the cluster index seek and all. But I see when I look at the execution plan, even though I have the partitioning column specified, when I look at the stats, it scanned all 39 partitions. And I was trying to understand why it did that. So I looked at the execution plan. It's a little bit easier to see here in the XML view of it, I'm sorry to say. But when I looked at the seek predicate, which you're going to see in the, what you call it, or when in the query plan, I saw this, the get partition range values with mismatched types, and the key there being mismatched types. And I'm not exactly sure why, but the SQL Server doesn't always get too smart when it comes using the partition column in terms of its data type. It does a better job, I think, of making argument, mismatched types sargable when you do just regular indexing. But the bottom line is that if I look at the the seek, again, I can't see it very well there. Go back to the XML. So the seek predicate always has the partitioning elimination as part of the first part here. There we go. Sorry. Yeah, so it has the, so it's basically doing a seek of everything, between 0 and 39 in terms of its partitions, followed by the, the seek, followed by the actual index columns that I have on that table and the customer ID and the order create time. So I was wondering why that happened. And then I said, well, let's see what happens when I go ahead and just explicitly cast it. That literal is the time. And then this time when I execute the query, just looking at the counts, you can see that it only scanned 5 partitions, which is what it needs for, the last, essentially it's the last few months plus, and such that greater than, I already have a partition for the future month. So it also includes the current month and the future month as well. So it touched only 5 partitions. So it helped out, the performance a bit of that query. But that's just one of those other gotchas I want to mention, is that when you're using Management Studio, just be careful of that. I generally would either use local variables like I did here to help mitigate the issue, but local variables are not parameters either. You know, you can get into, you know, the proverbial parameter sniffing issue. I won't detail in a whole lot, but here at least I get essentially the same plan, which is just a clustered index seek. But this time, if I look at the XML, you'll see I just see arranged partition new. I don't see that mismatch type ugliness like I did before. And same thing with just array, and this is really the right way. If you want to make sure that the query plan that you see in SSMS is the same as what your parameterized application is running, I recommend that you actually just use, you know, SB execute SQL. So here I just include the actual plan, and it's the same as I saw with the local variables in this case. Okay, going to be running over a bit, so I'll try to make it a little quicker here. Okay, yeah. So in this case here, I do not have a, you know, the partitioning column in the where clause, so it has to access every partition in the table. But because I have an index on, you know, the customer ID in this case, you know, it still has to touch all 39 partitions, but, you know, the logical reads is roughly about, you know, 2 or 3 logical reads per partition, because, you know, you know, in order to retrieve the data. And here I think it returns I have 100 orders for this customer, so, you know, it's distributed evenly among the different partitions with, you know, 3 or sometimes 4 orders, I think. So in this case here, with an aggregate query where I don't need the detailed data, but I need to do a full scan of, or should I say, you know, for the where clause is really based on, you know, things that are not indexed. So the only thing to help this query at all in terms of performance is the, you know, the partitioning itself, because there is no index to support this query. So in this case here, if I look at the plan, it has to do a, full, you know, clustered index scan of, you know, essentially all the partitions. You know, there's, let's see here. Yeah, so he's 13, I want to say 13 scans. Oh, I take it back. Yeah, it was, what you call it, it didn't have to scan all of them. It was able to eliminate the partitions that are not needed here, but it did have to do a full scan of each of those partitions that it did touch. And because it was parallel, you can't really tell from looking at the plan here how many partitions were touched, because you can have one thread, you know, scan multiple partitions, or 2 different threads scan the same partition concurrently. So running over, so I'm going to go over these very quickly. For partitioning table considerations, you have to remember there are some restrictions around it. The partitioning column has to be part of a primary key if you have a primary key on the table. It has to be part of all unique constraints if you have unique constraints, or unique indexes. So that's a requirement. It's also going to be implicitly added as an included column to non-clustered index, unless you already have the partitioning column in the key. So the fact that it has to be part of the primary key means that, you know, if you have an existing data model and you want to partition it, and let's say your existing primary key is an identity column or something that doesn't really lend itself to partitioning very well, if you need to keep the existing primary key, your only choice there would be to make it a non-aligned index. In other words, a non-partitioned index, so that you know, you could still satisfy your unique constraint on the primary key, but then of course you would have to forego a lot of those other benefits to partitioning, like being able to use the partition-level truncate switch. So as an alternative, you may want to tweak your data model to, you know, instead of just having a primary key of, let's say, your identity column alone, have a composite key on both your identity column and your partitioning column. But of course, you know, if you have an existing app, that might be, you know, somewhat problematic. So you know, it's not going to be a perfect fit for every situation. As I mentioned, performance can get, you know, worse if queries don't specify the partitioning column, and that indexing is, you know, important. So I'll jump through, you know, past a lot of these other slides here. Interesting, but because of the late start, I'm not going to have time to really touch on that. But I do want to mention something about the partition maintenance, you know, which unfortunately with SQL Server, it's not declarative. So you can't just say, hey, give me a 12-month, you know, monthly sliding window. You have to actually write script to slide that, you know, and usually one will schedule that with the SQL Server agent job to run either daily or monthly or whatever. And it requires some engineering to do so. It's not complicated stuff, but you need to be aware of a few things. First of all, you don't want to split a partition if it requires data movement to or merging a partition because it requires about 4 times the logging of a normal DDL operation. So when you think about it, if it takes, you know, an hour to do a delete statement of 100 million rows, then it'll take probably 4 times that all if you were to split a partition or merge one that has that many rows in it, mainly because of the logging and complexities. So usually a lot of the guidance you see from the Microsoft documentation will advise you never split empty partitions unless they're empty. And same thing with merge. And some go so far as to say even the adjacent partitions, make sure both the left and the right side of the boundary you're merging are empty. Technically, you don't have to quite go that far. And I'll show you that in the partition maintenance script, but just be advised that you want to avoid data movement. And if you do need to do data movement, like in the scenario we talked about earlier with the you know, merging or basically changing a month of daily partitions into a single partition for 1 month, it'd be better to just switch all those daily partitions out of the table and then just do a create index with drop existing on to you know, in your staging table. You know, then you can, you know, merge all the partitions in the primary table so it looks exactly like the staging table's partition function, and then just switch the data back in. And of course, don't forget to update statistics after you do that. Just like truncate, you can't have, you know, with switch, you can't, you can't have it, the table can't be referenced by foreign key constraints. Let's see, I think that's much it. I'll skip up to the last demo here, which is just the partition maintenance. I had these dropped off, drop them just in case. Not sure. Yep, didn't have them dropped. All right, so here I'm just creating a couple. These are based on just date, not date time. So I just create an empty, basically a partition function with no boundaries, everything to the primary file group for the partition scheme, and then you know, just a script that's starting from 12. This is for, you know, 12 months. So I have 12 full historical months this month, and I'm sorry, and then through next month. So if I run this, it'll create the you know, the partitions that we need. Create a table. I'm lazy, so I didn't even bother to create an index on there. It's just a heap. Let's just do, you know, show, you know, the partition function. Let me show the partition scheme that got created, or partition function, I should say. That's really what's. Yeah, so we have partitions starting from last year, June, all the way till next month. So that's what that script actually ended up doing. So now if we want to purge, expired data, so let's say this is next month. So I'm kind of cheating a little bit here, but let's see if I did that right. Yeah. Yeah, so what I'm doing here is I'm just checking to see, hey, do I have an index for the old, or a partition for the oldest retained date? And here I was, because this is all based on the current date, I just cheated and I went back another month. So this actually created a partition, for May of 2022 here. Just for demo purposes. But then what I do is I truncate the oldest partition, which is going to be not have any data in it in this example here. But then it just does the merge range. Then finally, just always truncate partition 1, which it should always be empty anyway. So I think I end up in the same spot basically. Yeah, so I already ran that partition. It really was a no op in this example here. But anyway, if by running that script, in a monthly job, then it can, well, I already have it here. So so that basically gets rid of the old data, and this part of the script will get rid of, or it'll create a new boundary for the next month if it's needed. But again, because I already ran that, it doesn't really need to do anything there. All right, I was running a bit over, so I didn't want to too much time. At the end of the deck, I do have a couple of links. One is just to the documentation, which is pretty good. I mean, I think Microsoft done a good job of beefing it up over the years, because originally it was kind of scant, and definitely beefed it up to include some best practices in it. And then I also have a link to one of my blog articles for best practices on table partitioning. So I'll open it up to any dangling questions here. Yes, ma'am.
Yes, you have the PowerPoint and your demo scripts available, or will they be available?
They will be available, of course. I'll the PowerPoint. I think correct if I'm wrong, Julie. We're going to upload the YouTube, right? The recording to out there, and then I'll provide you the link for the PowerPoint and the demo scripts that I went through today too. Yeah, unfortunately, I'm always having a problem finding a good place to host those things, but I'll try to make sure that gets disseminated this time.
Dan, I'll put on our meetup page, I'll say, the recording's available, here it is, and then whenever you get your GitHub or wherever you put it, I'll put, the PowerPoint examples or something.
All right, thank you. Perfect. All right, any other questions?
You mentioned having table partition, the partitioning column as part of the primary key. What if we don't have a primary key? What if we just have like a column store index instead of a store?
Yeah, I didn't cover column store specifically in this one. I had one of the slides I kind of had to go past. Yeah, there is any special indexing requirements for partition tables. So if you don't have a primary key, and in other words, if it's not a true relational table, that's okay. You can still partition it. And that one demo I did, I just took a good old-fashioned heap and just partitioned it. There's nothing to stop you from doing it. Although I'm biased. I don't like heaps. I like tables with clustered indexes. almost exclusively, with the exception of a staging table, of course, that kind of stuff. But yeah, I recently had a project where I had to clean up a big partitioning mess, and it was every anti-pattern you could find. No, it wasn't it was just out of ignorance. It's nothing, it's just DBA had not done partitioning before, and, Googled stuff up, you find some scripts. Hey, you got to create these yearly file groups. Yeah, here's my range left partition scheme based on date. So the queries were hitting 2 partitions when they only needed to hit 1, all that kind of stuff. That's so common because, until you've done it and experienced those. And that's why I wanted to try to underscore some of those things here.
Just the reason I asked it also is that normally OLTP systems, we want to use stuff that are, if I were doing it, I would do for OLTP, of course, every single time primary key and then not unless you're indexed to cover it. But if it is an OLAP system, a lot of times it's aggregated to a certain extent that it's hard to have that. And like a column store where it's because people are trying to just do analytics out of aggregating values and you're not really using, you don't have like row level information. So partitioning even in those cases could be helpful based on the type of aggregate. So I just didn't know.
Yeah, there's a lot of details that go into the column store stuff, especially when you talk about the elimination of the segments and all that kind of stuff, and then having partitioning on top of that. But the partitioning elimination would happen before it starts looking at the the metadata for the column store to determine which row groups it has to grab and stuff. All right. Sorry to go so long, but I think it was good stuff. Wish I could have done a little bit more on the presentation.
Thank you.
All right.
Thank you, Dan. Thank you so much. Really appreciate it. Thank you.
All right.